Oscillatory motion occurs when a system is displaced from an equilibrium position and experiences a restoring influence that acts to return it toward that equilibrium. The essential idea behind oscillations is not periodic motion itself, but stability. An equilibrium is stable if small displacements produce forces or accelerations that point back toward the equilibrium position. Whenever this happens, overshoot is unavoidable and oscillation naturally follows. This idea appears across physics. A mass on a spring oscillates because stretching the spring produces a force pulling it back. A pendulum oscillates because gravity produces a torque that restores it toward its lowest point. Even electrical circuits and molecular vibrations behave as oscillators under the right conditions. What unifies these systems is not their physical construction, but the mathematical structure of their restoring behavior. In many systems, for sufficiently small displacements, the restoring force is proportional to the displacement itself. This is not an assumption, but a consequence of Taylor expansion. Near equilibrium, almost any smooth restoring force can be approximated by a linear term. When the force is proportional to displacement and directed toward equilibrium, the motion that results is called simple harmonic motion. Understanding oscillations is important because they represent how systems respond to disturbances. Oscillations tell us how energy moves, how systems store and release energy, and how they respond to external influences. They also provide one of the clearest bridges between physical intuition and differential equations. To describe simple harmonic motion quantitatively, we begin with the simplest physical model, a mass attached to an ideal spring. The defining relationship for an ideal spring is Hooke's law, which states that the force exerted by the spring is proportional to the displacement from equilibrium and directed opposite that displacement. In words, force equals minus k times x. The constant k measures the stiffness of the spring. Applying Newton's second law, force equals mass times acceleration, we obtain the equation of motion. Substituting the spring force gives m times x double dot equals minus k times x. Rearranging yields m times x double dot plus k times x equals 0. This is a second-order differential equation that completely determines the motion of the system. What is remarkable is that this equation does not depend on how the system was displaced. It depends only on the physical properties of the system, the mass, and the spring constant. The solutions to this equation are sinusoidal functions, meaning the system oscillates indefinitely between positive and negative displacements. The general solution is x of t equals a, cosine of omega t plus phi. The amplitude a represents the maximum displacement from equilibrium and is determined by initial conditions. The phase constant phi encodes where in the oscillation the system begins. The angular frequency omega equals the square root of k over m and sets the time scale of the motion. This frequency is not chosen arbitrarily. It emerges from the balance between inertia, represented by mass, and restoring strength, represented by stiffness. A stiffer spring oscillates faster. A heavier mass oscillates more slowly. This relationship appears repeatedly in physical systems and provides deep insight into how competing effects determine motion. To describe simple harmonic motion quantitatively, we apply Newton's second law. Force equals mass times acceleration. Substituting the spring force gives m times x double dot equals minus k times x. Rearranging yields m times x double dot plus k times x equals 0. This equation is a second-order differential equation. Its structure tells us that acceleration depends directly on position rather than velocity or time. The equation itself contains no information about how the system was initially displaced. Instead, initial conditions determine the constants of the solution. This equation is the mathematical heart of simple harmonic motion. Every result about oscillatory motion flows from it. The solution to the simple harmonic motion equation is sinusoidal. The general solution can be written as x of t equals a cosine of omega t plus phi. The amplitude a represents the maximum displacement from equilibrium. The phase constant phi encodes the initial conditions, determining where in the oscillation the system begins. The angular frequency omega is equal to the square root of k over m. This quantity determines how rapidly the system oscillates. It depends only on the physical parameters of the system, not on how far the system is displaced or how fast it is initially moving. This result highlights an important physical idea. Oscillatory systems have natural frequencies set by their internal properties. Velocity and acceleration are obtained by differentiating the position with respect to time. Differentiating the position once gives velocity. Differentiating again gives acceleration. The key result is that acceleration equals minus omega squared times x. This equation shows that acceleration always points toward equilibrium and is proportional to displacement. This restoring nature of acceleration is what sustains oscillatory motion. Whenever acceleration points back toward equilibrium, overshoot is inevitable, and oscillation follows. Simple harmonic motion can also be understood using energy. In an ideal system without damping, mechanical energy is conserved. Energy continually transfers between kinetic energy and potential energy. At maximum displacement, the velocity is zero and all energy is stored as potential energy. At equilibrium, the displacement is zero and all energy is kinetic. Between these points, energy is shared between the two forms. This exchange repeats indefinitely. Viewing oscillations through energy provides insight into amplitude, stability, and system behavior without directly solving differential equations. In real systems, oscillations do not continue forever. Energy is lost through friction, air resistance, internal deformation, and other dissipative processes. These effects are modeled by damping forces, which are often proportional to velocity. A common damping force is written as force equals minus B times V. Including this force modifies the equation of motion to m times x double dot plus b times x dot plus k times x equals 0. This new equation reflects the competition between restoring forces, inertia, and energy loss. The behavior of a damped system depends on the relative strength of damping. If damping is weak, the system oscillates with gradually decreasing amplitude. This is called underdamped motion. If damping is exactly strong enough to prevent oscillation while minimizing return time, the system is critically damped. If damping is stronger than this, the system is overdamped and returns to equilibrium slowly. These behaviors are not arbitrary classifications, but emerge from the mathematical structure of the equation of motion. When an external force acts continuously on a system, the motion is called forced oscillation. A common driving force is sinusoidal, written as F0 cosine omega t. This force continually injects energy into the system. After transient effects decay, the system reaches a steady-state motion that oscillates at the driving frequency rather than the natural frequency. The amplitude and phase of this motion depend on the driving frequency. Resonance occurs when the driving frequency approaches the system's natural frequency. At resonance, energy transfer from the driving force to the system is maximized, producing large amplitudes. Damping limits the maximum amplitude and shifts the resonance frequency. Resonance is central to engineering, physics, and design because it can either be exploited or must be avoided. Electric charge is a fundamental property of matter. Charges exert forces on one another through electric fields. Like charges repel and opposite charges attract. These interactions occur even when charges are not in contact. To analyze these interactions, we introduce the electric field as an intermediary concept. The electric field is defined as force per unit charge. It describes how a test charge would experience force at a given point in space. The electric field exists independently of whether a test charge is present. This concept allows us to describe interactions in space rather than between individual particles. A point charge produces a radial electric field with magnitude equal to K times Q over R squared. The field points outward for positive charges and inward for negative charges. This inverse square behavior reflects how the field spreads through space. When multiple charges are present, the total electric field is the vector sum of the individual fields. This principle of superposition means fields add linearly. Each field is calculated independently, broken into components, and added to obtain the net result. When charge is distributed continuously, sums become integrals. Charge density describes how charge is distributed along a line, surface, or volume. Symmetry plays a crucial role in simplifying calculations and determining which components of the field survive. Electric flux measures how much electric field passes through a surface. It depends on the magnitude of the field, the area of the surface, and the orientation between them. Only the component of the field perpendicular to the surface contributes to flux. Flux connects electric fields to geometry. Gauss's law states that the total electric flux through a closed surface equals the enclosed charge divided by epsilon zero. This law is a statement about how electric fields originate from charge. It is more fundamental than Coulomb's law and applies universally. Gauss's law is most useful when symmetry allows the electric field to be constant over a closed surface. Spherical symmetry applies to point charges. Cylindrical symmetry applies to infinite lines. Planar symmetry applies to infinite sheets. Choosing the correct Gaussian surface is a geometric decision guided by symmetry. Using Gauss's law, electric fields can be derived for spheres, cylinders, and planes. These results reveal how field strength depends on distance and charge distribution. Gauss's law simplifies problems that would otherwise require complex integration. Electric forces can do work on charges, changing their potential energy. Electric potential energy depends on the positions of charges and the work required to move them. Energy methods provide powerful alternatives to force-based analysis.